All right, here's the partial fraction decomposition homework. As you see, there's only 4 questions on here, and that's because partial fraction decomposition, frankly, it takes a little while. If you find yourself needing more practice, there's lots of examples in the book that you can work out. But my hope was that 4 would be enough, that if you do at least 3 of these for full credit, 4 for extra credit, you'll have the skills necessary to do this, and I'm not just wasting your time. I don't know. It's always kind of a balancing act in terms of how many homework problems I assign, and I try my best not to give you too many, but to give you enough where you can learn the topics. Hopefully I did okay here. At any rate, 4 questions. The nice thing about a really short number of questions is kind of like in the previous video, 3 is required, and 4 out of 3, that's 133%. You could really boost your homework average if you do all 4 of these if you decide you want to. The first 2 questions are pretty similar. In both cases, I think what you'll see is the denominator factors into linear terms. So since this is a second degree polynomial, it's going to factor into a product of 2 different linear terms. And since this is a third degree polynomial, it's going to factor into a product of 3 different linear terms. And this one will be kind of like one we did in the video where you note that all 3 terms have an x in them. So first pull out that x, and that will leave you with a second degree trinomial, which hopefully you can factor. This one starts you out with the second degree trinomial, so again, hopefully you can factor it. If I gave you something on the quiz, it would probably look like one of these 2, except I would start out with the denominator all factored for you, so you wouldn't have to do that factoring step. And I'd also choose numbers up in the numerator that are a little bit smaller just to try to make your life a little bit easier. If factoring is a problem for you, it really is something you should be able to do in this class, even if I'm not going to test you on it. So at the end of the video, I'm going to take one of these with the worst numbers. I guess that's this one right here. And I'm going to show you a method for factoring this. I mean, if you're just looking for the answer, you can kind of cheat. You can Google this stuff if you need to. But I think it would be good for you to have the skills to be able to factor something like this at this point in your math background. So if you want a little practice with this, I'll show you how to do it at the end of the video. For the sake of the homework, feel free to Google if you want, if you need help on this kind of stuff. But yeah, questions 1 and 2 should be straightforward. They factor into linear terms. So that's the a over the first term, b over the second term here, and a over the first term, b over the second, c over the third here. Solve for a, b, and c, take your antiderivatives, and you'll get your answer. And note up here, for the natural log, I think on a lot of the homework problems, they let you get away without putting the absolute value symbol in there. But you really should have the absolute value symbol on all your natural logs. And on this one, it's implying that you really do have to put it in, or it might mark it incorrect. Question 3 is a little bit different than the first 2. And the idea with question 3 is it's very similar to one of the examples that I did. But if you factor out an x from each of these terms, you're left with x squared plus 3. And I think the example that we did, it was x squared plus 1 instead of x squared plus 3. But both x squared plus 1 and x squared plus 3 are what are called irreducible quadratic factors. And so what that means is you can't factor that any further. So this denominator completely factored is x times x squared plus 3. And the fact that one of those 2 factors are quadratic means that you're not just going to put an a over the top of it or a b over the top of it or something. You'll put an ax plus b or bx plus c, depending on what letters you choose there. So be a little careful with that on question 3. The good news on question 3 is it looks like they kept the numbers a little bit more manageable. Maybe that makes this one a little bit more like the type of thing you'd see on a quiz. Question 4, kind of like question 3 in that it involves an irreducible quadratic. This one's kind of a mess. I mean, 4th degree, that's just going to be a lot. I think what you'll see on this one is they start you out with a difference of squares. So like just how you can factor x squared minus 9 into x plus 3 times x minus 3. You can factor differences of squares into a product of what are called conjugate pairs. You can do that same trick here because this is a perfect square. It's x squared times x squared. And this is a perfect square. In my version, it's 16 times 16. And so I think what will happen is they'll give you a number here, and this number here will be some other number to the 4th power. And what that means is you'll have a difference of squares. So in my case, I'd factor this to be x squared minus 16 and x squared plus 16. And the x squared plus 16 is an irreducible quadratic factor, just like the x squared plus 3 and the x squared plus 1 that you saw in the video. But the x squared minus 16 could be factored again because it's, again, a difference of squares. In that case, it would be x plus 4 and x minus 4. So I know your numbers might change, but for my numbers, when this is completely factored, you'll have 2 linear terms and 1 quadratic term, 1 irreducible quadratic term. And so that will inform how you choose your A's and B's and C's and D's. And if you solve for A, B, and C and D, you can get the answer that goes up here. And then if you integrate this, you'll get the answer that goes down here. So just to be clear, on all 4 of these, you do the same thing. You do all the algebra work up here, which I kind of like that they check your answer in that step, and then you do the calculus down here. Because if you make one little mistake, say in the calculus, it'd be a bummer to have to go all the way back and double check that crazy algebra you did to do the partial fraction decomposition. So at least there's a little check mark halfway through the problem. All right, now before I end this video, what I'm going to do is I'm going to take this problem right here, this denominator, 30x squared plus 89x plus 63, and I'm going to factor it in front of you. So before I factor this problem that I mentioned from the homework, I want to start with a really easy one to illustrate the method that I think might help you in factoring more difficult ones. And the idea with this method is you don't really need it on these easier problems. Most people can get around this just by guessing and checking, being like, well, I need the product of the coefficients on the x's to be 2, so I guess one of them is a 2x and the other one is an x. And then I need two numbers that multiply together to give me 3, so it's 1 and a 3, and I just have to figure out which goes in which spot. Well, let's see, if the 3 is here, I get 3x plus 2x, which is only 5x. That's not right. So there must be the 1 here and the 3 here. Most people can factor quadratic trinomials where the leading coefficient is not 1. Those are kind of the harder types. If the numbers are easy enough, just using this kind of guess and check method. But the problem is the guess and check method ain't going to get you very far over here. Right? There's so many different options of numbers that multiply to 30 and 63 for that matter, that you're going to have way too many options realistically to figure out which one works to get you the 89x when you sum up the O and the I in FOIL. So rather than do this guess and check method over here, something that you can do, which is a bit overkill in this problem, is your first step is to find two numbers, and those two numbers have to add to whatever the coefficient on your linear term is, this 7 right here, it's often referred to as b, and they have to multiply to whatever the product of your leading coefficient and your constant term are. So 2 times 3 gives me 6, so that 6 goes right here. So I need to find two numbers that when I add them together it gives me 7, and when I multiply them together it gives me 6. It's easier to focus on the multiplication rather than the addition, because lots of different pairs add to 7, but not that many add to 6. For 6 it's either 1 and 6 or 2 and 3, right? And 2 and 3 add to 5, so that ain't it. But 1 and 6 add to 7, so the answer to this first step is 1 and 6. But that's not it. That's the answer to just the first step. Then you move on to the second step. And what you do in the second step is you replace your linear term here, the 7x, with two terms where the coefficients on those two terms are just the numbers that you found in step 1. So what I'm saying is 2x squared plus 7x plus 3 is equal to 2x squared plus 1x plus 6x plus 3. Right? You just rewrite your original equation, but instead of writing 7x, you write 1x plus 6x. And note the order is not important. You could have made this 6x plus 1x if you thought about 6 and 1 as the answer here as opposed to 1 and 6. But if you replace 7x with 1x and 6x, you're coming up with something that's equal to this, and it has to be equal because these two numbers that you found, they add to 7, so it makes sense that you can change this 7 into a 1 and a 6. At any rate, that's all you do in your second step. Your third step is what's called factor by grouping. The advantage of having 4 terms here is you can use this method called factoring by grouping. And normally when you're thinking about factoring, you look at all 4 terms and you're like, what do all 4 terms have in common? But all 4 terms don't have anything in common. So instead of doing that, what you do is you factor by grouping. You make the first 2 terms your first group, and then the second 2 terms your next group. And you just factor those individually. So what I'm saying is you look at this first group and you ask yourself the question, what do they have in common? And their coefficients don't have anything in common, right? There's no number that divides evenly into 2 and 1, other than just 1. But they do both have an x in them. So all you can factor out is the 1x. And so you factor out a 1x from these 2 terms, and you're left with 2x plus 1. Right, x times 2x plus 1 would give you the 2x squared plus the 1x. This 2x plus 1 becomes what I refer to as the target. So what you want to do now is you want to factor something out of your second group so that you're left with this same target over here. And it'll always work out. If you chose these numbers correctly, there'll always be something that you can factor out of your second group to recover this target. So in this case, it's a positive 3 that I can factor out for my second group that will leave me with a 2x plus 1 behind. So I get this far. I'm not done factoring my grouping. Now I think about this as 2 terms. The first one is all this stuff. The second one is all this stuff. And I ask myself the question, what do they have in common? And by the way I've done this, they have to have the target in common. They have to. Right? Because the target is what I made sure appeared in both of these terms, so it has to be in common. So you take that target and you factor it out in front, that 2x plus 1. If I've taken this out in front and this out in front, these aren't there anymore. So all that's left behind is the x and the 3. What I get is x plus 3, which, by the way, is exactly what I used to have written up here that I could get without this method in this specific problem because these numbers were so easy. At any rate, that method will help you factor over here. Really, the only thing that's brutal over here is these numbers are so bad, so it's going to make the first step a little bit harder. But let me give you some advice on the first step. So I do the same thing. I need my numbers not to add to 7, but instead to add to 89. I need them to multiply 2, and you're like, oh man, I don't know what 30 times 63 is. Or maybe you do. But don't worry what 30 times 63 is. Instead, think about their prime factorization. So 30 is 3 times 10, and 10 is 2 times 5. So 30 is 2 times 3 times 5. And 63 is 9 times 7, but 9 is 3 times 3. So 63 is 3 times 3 times 7. So what I'm saying is I need them to multiply 2 the product of all these numbers. And you don't even have to worry about what the product of all these numbers are. These will be kind of the pieces that you use to make 2 different numbers that add up to 89. So what you have to do is kind of partition these into 2 different groups. So for example, let's just try putting them back the way they came. Let's take these guys as one group and these guys as another group, just totally arbitrarily. If I multiply the 3 of these together, 2 times 3 times 5, I get 30. Oh, right, of course I got 30. That's this 30. And if I multiply the 3 of these guys together, I get 63. Of course I got 63. That's where these numbers came from. And then 30 plus 63, that's 93. Oh, bummer, that's not 89. So what that means are these are not the 2 numbers that I'm looking for in step 1, right? Because these add up to 93 as opposed to 89. However, you can learn from this. If the number you got when you added these up is too big, then what you have to do is make these numbers closer to each other. So what I'm saying is maybe I can make this number a little bit bigger and this number a little bit smaller. If the number that I got when I added these up was too small, like say I added these up and I only got, I don't know, 84 or something. If this plus this were 84, well then that would tell me that I need these numbers to be further apart from each other. So if I need the sum to be smaller like I do here, I need these numbers to be closer together. How can I make them closer together? Well, maybe I swap out, I don't know, this 5 and this 7. Let's see what that does. Right? So if I did 2 times 3 times 7 on this side, and then 3 times 5 over on this side. 2 times 3 is 6, times 7 is 42. 3 times 3 is 9, times 5 is 45. Let's see how that works. We don't even have to worry about multiplying them because we know they multiply to the same thing because we're taking the exact same parts. All we got to do is add them up. And 42, 45, that's 87. Oh, shoot. Up here, I was a little bit too big, right? These were equal to 93. Up here, I was a little bit too small. These are 87. So I need something in between the two. I need this first number to be something in between 30 and 42. Well, let's see. I could make this number 35 if I wanted to, right? This 5 and this 7. So if I chose 5 and 7 over on this side, I'd get 35. And if I used up the 5 and the 7, what I have left is a 2, a 3, a 3, and a 3. If I'm taking all these different parts, 3 to the 3rd power is 27 times 2 is 54. And let's see, 35 plus 54. Oh, hey, that's going to work, huh? 35 plus 54 is 89. I'm really happy I found my pair. So this little trick that you can do with prime factorization will work. And it might feel like just this blind hunt where you can't figure anything out. But if you recognize that if these numbers, when you add them, are too big, that means these two things are too far apart. And the way you can remember that is if you took all of these numbers and created one of them. So if I took all of these and put it over here, then my other number would just be a 1, right? Because 1 times all of these numbers would multiply to the product of all these numbers. But if you think about what the sum of that would be, it would be huge, right? Because if 1 plus this huge number that I get when I multiply all these together would be way too big. So if I get a number that's too big, that means these two guys are way too far apart, so I need to make them closer together. That's the way I remember it anyways. And that's a method that you can use to factor these ridiculous polynomials. I guess I should finish at this part, but once I finish step 1, really it's not too bad. The two numbers that I found are 35 and 54, so I would say 30x squared plus 35x plus 54x plus 63 is what I get at the end of step 2 when I replace my middle term with the two new terms that I created from the numbers that I found in step 1. And then I factor by grouping this first group. They both have an x in them, but more, they're also both divisible by 5. So I can pull out a 5x from this first group, and then I'm left with 6x plus 7, right? 5x times 6x gives me 30x squared. 5x times 7 gives me 35x. And then I stare at this next term, and I'm like, how do I recover this product? What can I factor out of this to be left with 6x plus 7? Well, 9 times 6 is 54. So it must be the case that if I factor out a 9, I'm left with 6x plus 7. Let's see, does that work? 9 times 6 is 54. 9 times 7 is 63. Yeah, that all looks good. And now what I have are two terms, and each of those terms have a 6x plus 7 in them. So I can factor out that 6x plus 7, and I'm left with 5x plus 9 as the other term. What I'm saying is this mess of a polynomial up here, it factors to just 6x plus 7 times 5x plus 9. I won't test you on this. It's the kind of thing that would be like an extra credit question in a pre-calculus class. And really, I want you to focus more on the calculus and less on the algebra. But it's a good thing to know. And it involves some kind of interesting topics, these ideas of prime factorizations and stuff. So no one ever taught it to me, so I figured I'd teach it to you guys.